have a wonderful speaker this morning. I'm sure a lot of you know that we have a great large number of graduate students at Scripps. In fact, I think at the moment we have more than we've ever had, 222 students. And this morning, Dr. Kerry Key is going to speak, and he got his PhD here at Scripps last year, so he's one of our newly minted rising stars. And his research interests are in the application of electromagnetic exploration techniques in the study of the crust and upper mantle at mid-ocean ridges. And this is very important for many reasons. It really allows us to study the structure, the geological structure under the Earth's crust, under the mantle. And it also might be very important applications for the geology of offshore petroleum prospects. So, without further ado, I would like to introduce Kerry, who's going to talk about exploring new fields, how marine geophysicists image the Earth's crust using electromagnetism.
Good morning. So as Nigella said, I just recently graduated. That was last November. I defended my PhD, and you have to excuse me if I sound a little tired this morning. I'm still getting used to getting up this early. I think it's typical for most Scripps grad students to not get up this early unless the surf is breaking really good. Okay, so I'm going to talk about imaging the structure in the Earth's crust in the oceans. Most of the Earth's crust is underneath the oceans, over 2/3 of it, and I'm going to talk about a new way that we're exploring the structure of the Earth's crust. It's really expensive to drill down into the Earth's crust to see what's there. So, as a Earth scientist, we try to think of different techniques for putting instruments on the seafloor and being able to see underneath the seafloor and into the crust to see what's there without having to drill. And the technique I'm going to talk about is an electromagnetic technique. So we use electromagnetic waves to image the geologic structure beneath the seafloor. And this technique is something that was invented, the theory was invented in the 1950s by a Frenchman, Louis Cagniard, and also a Russian. Both A.N. Tikhonov invented this technique, and they both did this simultaneously at the same time. The theory's been in place for over 50 years now, but the instrumentation and the computational power to actually compute Earth models from this type of data has just recently come up to speed to where we can actually image two-dimensional and three-dimensional features of the Earth. So, it's a new emerging field. It's pretty exciting because it's new. There's a lot of discoveries that are yet to be made by using this technique. And I'm going to talk about two applications of this technique that I did for my PhD thesis. One application was imaging the geologic structure associated with the petroleum reservoir offshore in the Gulf of Mexico. And the other one is imaging the magmatic system at a mid-ocean ridge. So mid-ocean ridges are where the crust of the oceanic crust is formed, and so it's important to understand where the magma is and how the magma interacts with the surface to form Earth's crust. Okay, so again, who cares about the crust beneath the oceans? Well, from the Earth scientist point of view, we're interested in figuring out how material that's down in the Earth's mantle comes up at an oceanic spreading ridge and it forms the Earth's crust. And at a spreading ridge, this material comes up, it cools and solidifies to form the Earth's crust, and then these plates spread apart. Later on, these plates subduct. This will be millions of years later. They can subduct beneath the continents. There can also be lava events and rifting on the continental crust that forms more continental crust. You can also have hotspot volcanism that comes up through the crust to form volcanoes such as places like Hawaii. And so all these processes are going on in the crust, and it's really important to understand these so we can understand how Earth, the different features that we see in Earth, and how these are going to change with time. There's also economic reasons to understand the features of the crust. So then this simple animation that I'm going to show you in a second here, we have some sedimentary layers in the earth here. Let's just say that this model, or this cartoon here is about 10 kilometers deep. So we have an ocean and some sedimentary layers shown as these striped layers here. We have some feature that intrudes these sedimentary layers and deforms them, and that's formed a petroleum reservoir here. So this is an offshore petroleum reservoir cartoon. And if you're a petroleum exploration company, you come along with your drilling ship, and you want to drill down and you want to hit this reservoir. It costs about $30 million or so is the average cost to drill a well in the ocean. And so, it's expensive to just go around blindly drilling, trying to strike oil. You really want to know what the features of the subsurface are, what the geologic structure is, and what regions are most likely to contain a petroleum reservoir. Okay. So some tools for exploring Earth's crust. Well, the predominant method that's been used for several decades now is the seismic method. And this method has the highest resolution. And the seismic method is where we send some seismic energy, so we send vibrations down into the Earth, and those vibrations travel with a speed that is indicative of the seismic velocity of the material that it's traveling through. So we can go and measure the seismic velocity of different rocks, and that's a proxy for the geology of the subsurface. And the technique I'm going to talk about or emphasize today is a new technique. It's an electromagnetic technique, so we use electric and magnetic fields. And that's called the Magnetotelluric method, or in short, the MT method, although it's not empty. And sorry for the bad pun there. This method is sensitive to the electrical resistivity of Earth materials. So resistivity is sort of the opposite of conductivity. So we're a wire that we use in electronics or to wire a light bulb to supply electricity to it. A wire is very conductive. Well, the insulation around that wire is very resistive. And so Earth structures are similarly, there's resistive Earth structures and there's conductive ones. And these can be used as a proxy for geology also. Okay. So here's a table just showing some seismic velocities and resistivities of marine rocks. So we have different types of rocks here, and also seawater. And here's the seismic velocity and the resistivity. And these are just some general figures to give you an idea of what we're trying to measure here. Where seawater has a velocity that's different from the rocks beneath it. Seawater is also much more conductive or less resistive than the rocks that are typically beneath the oceans. But one of the interesting things about resistivity is that if you add seawater to something like sandstone has a lot of porosity in it, and so you can fill that pore space with seawater. Well, that lowers the resistivity of the sandstones. So we can also use resistivity as a measure of how much seawater is contained in a sandstone and things like this. There's also features like halite, which is rock salt, and this is important for petroleum exploration because rock salt is typically located in offshore sedimentary areas where we find petroleum reservoirs. And halite has a much higher electrical resistivity than seawater saturated sandstone, so it forms a contrast in resistivity, which is a target we can image. If we look at rocks that you would find on the mid-ocean ridges, like basalt, which is the majority of Earth's crust is made of basaltic composition. Basalt has a fairly high resistivity, but as soon as you melt it, it has a low resistivity. So molten basalt or lava is a very good target for us to find using electrical methods. So I'm going to take a step back here and just try to explain a little bit more about the actual fundamental techniques here and how you can visualize these. So again, we have our this is a salt intrusion here. It's to form these sediments, and we have a petroleum reservoir. And one technique for imaging this structure is the seismic reflection method. And so I'm going to show a little cartoon of that here. So in the seismic reflection method, we have a boat towing an array of receivers and an air gun. The air gun lets off an explosion, and that shock wave propagates down through the Earth, and it reflects off the different layers. And we measure those vibrations on an array of receivers here. So we know when the shot fired, and we know when we record the time that we measure these impulses back here, and we can use that to reconstruct the geologic structure of the subsurface. And so this is what a seismic reflection profile looks like. This is what the end result of this type of experiment looks like. So we have, this is depth here and position. So this is about 9 kilometers deep and about 15 or so kilometers wide. And you see that there's no reflections here in the upper kilometer. That's because it's going through the seawater and we don't get any reflections back. And then each one of these stripes down here is a reflection from a different layer in the geology. So this is over a sedimentary section on the continental shelf in the Gulf of Mexico. And there's lots of different layers of sandstones and shales and things in here, and each one of those gives a reflection. So you can see that we've got a profile here of what the subsurface geology looks like, and there's an exceptionally bright reflection here. And this bright reflection is from the contrast between sandstones and shales and muddy type rocks, and then rock salt, which is shown by this bright reflection here. The sandstones and shales have a very low seismic velocity, and the salt has a very high velocity, and that contrast creates a very bright reflection. The other technique that we use for this is the magnetotelluric method, and this is the electromagnetic technique that I've been talking about. So here's a little cartoon illustrating that technique. For this one, we put an array of receivers on the seafloor, and at the end of these little spider-like arms, we measure electric fields, and there's also magnetic field sensors contained in these instruments. So the source field is a natural variations in Earth's magnetic field. These are about 10,000 times weaker than the main magnetic field of the Earth, and those propagate down into the Earth, and they induce an electric field. And the strength of this electric field is proportional to how resistive the Earth is. So we measure both of these fields on the seafloor with these instruments, and that shows us, and that contains information about how well electricity can flow in the subsurface. So again, we have a natural source magnetic field that propagates down into the Earth, and that induces an electric field in the ocean and the seafloor. And when you have structures like this, like strong conductivity contrast, that causes what we call secondary electric and magnetic fields, and you even get charges building up on the sides of these features. So we can take these electric and magnetic fields that we measure on the seafloor and create a resistivity profile of the Earth. Go on to the next slide. Okay, so the end result of this type of experiment is a profile, which is the electrical resistivity of the Earth versus depth and position. So we're going down about 9 kilometers here, and about this profile here is about 20 kilometers wide. The blue colors mean that the Earth is resistive and electricity doesn't flow that well, and the red colors are areas where the Earth is conductive and electricity does flow well. So again, you can see that we're getting this resistive feature here and relatively conductive zones around it, and then deeper down the resistivity increases even more. So this is a proxy for the geology. And this actual model is from the same area that the seismic data was. So you can see that where the bright salt reflections in the seismic data were occurring, we're getting this resistive feature. So there's a bit of agreement between the two methods. Okay, so the technology to do this type of imaging of the crust using the electromagnetic method is something that was invented at Scripps. It started out in the late 1980s with Jean Fiu and Charles Cox inventing a seafloor electric field and electromagnetic receiver, and in the mid-90s was improved upon by my PhD advisor Stephen Constable. And this is the end product, is this system here, which is an autonomous seafloor electromagnetic receiver. We have big long arms that stick out the side of the instrument here, and we put electrodes at the end. And that's how we measure the electric fields. So we can measure electric fields in this direction and this direction at the end of these long arms. These blue sensors here are magnetic field sensors, and these sense magnetic field variations that occur at a period of about 10 hertz to about 10,000 seconds. So we call this a long period signal. The vehicle is attached to this very large concrete anchor. This is about 200 kilograms, and that keeps the magnetic field sensors very stable on the seafloor. If the instrument were to vibrate or wobble around on the seafloor, we would measure that on the magnetic field receivers, and that would be noise in our data. And the instrument is held to this concrete anchor by this mechanical release system here, and we can control that by sending signals from the ship down to the instrument, and at the end of the experiment, this release will let go, and the instrument will float back up using the flotation that's provided in glass spheres here. The data from these sensors is recorded on a data logger in here. So this is basically a computer, and we can record data for up to several months on this system. We also have a flag for when the instruments come back to the surface, because it's, these glass balls are in the yellow cases here only float about 6 inches above the surface of the water, and so you really need a flag to spot these things when they come back to the surface. We also have a separate float here that detaches from the main bundle of floats, and this is called the stray line float, and it's attached to the instrument with a 10-meter long tether, and we can throw a grapnel hook and from the boat to grab this tether and then pull the instrument back onto the ship. And this stray line float has a radio beacon and a strobe light, so whether it's foggy or nighttime, we can find where the instruments are floating on the surface. So this is a picture of one of our receivers on the seafloor. This is just offshore the Scripps pier. We were doing an experiment off the end of the pier, and so Steve Constable dove down on the instrument and took a picture of it. So you can see the large concrete anchor and the glass floats, the data logger, and then the arms that contain the electrodes. So one of the things that Scripps has built its reputation on is its instrumentation. There's a lot of very talented scientists and engineers at Scripps who are very good at building marine instrumentation. And in the Scripps Marine EM Lab, which I'm part of, we've had a collaboration with the petroleum exploration industry to develop this marine EM equipment. And we've been able to build up a fleet of 40 of these seafloor electromagnetic receivers. This is sort of unprecedented or unrivaled in the academic world. This technology was, we started building this around 1995. Now, nearly 10 years later, there's now 3 commercial exploration companies in the petroleum industry that are using this technology. So if you look around in the petroleum exploration industry, you'll see pictures of seafloor electromagnetic receivers that look suspiciously similar to ours, and that's because they're all derived from the Scripps Marine EM instrument. We've had over 1,000 deployments of this system. Some of these experiments have been academic experiments at mid-ocean ridges, trying to understand the dynamics of plate tectonics, and the other experiments have been to do petroleum exploration. Some of the petroleum experiments have been like offshore Norway. We did some experiments with Statoil. There was an experiment in between the Shetland and Faroe Islands on some petroleum reservoirs there. And we've had a lot of experiments offshore West Africa recently. That's a big area for oil and gas exploration right now. We've also had several experiments in the Gulf of Mexico, a few experiments offshore San Diego, and one that I'll talk about later today is one here at the East Pacific Rise, which is along this mid-ocean spreading ridge here. So this is a ridge where Earth's crust is formed. So we measure magnetic fields, which are represented by this H. We measure that on the seafloor, and we also measure the electric fields. And they're related to each other through this quantity Z. And Z is basically, you can think of that as the resistivity, the electrical resistivity of the Earth. So we measure H, we measure E, we can calculate what Z is. And so this is an example of what the data looks like. I thought I'd show some data. This is about 15 minutes worth of data for 2 sites. So we record 4 channels of data at this site and 4 at this site. So 2 separate locations, the same time. These top 2 channels are magnetic fields, and these bottom 2 are electric fields. And you can see that the magnetic field and the electric field are highly correlated. There's these little wiggles. And this signal, in fact, I forgot to mention this, but the signal for this, the magnetic field signal, is caused from the interaction of the solar wind with Earth's magnetic field. The sun is constantly emitting charged particles, and these particles interact with Earth's magnetic field and cause these little pulsations. And these pulsations are about 10,000 times weaker than Earth's main magnetic field. But we have very, very sensitive receivers, and so we're actually able to measure those tiny pulsations. And so those pulsations, magnetic pulsations, cause these electric fields. And again, they're related by this relationship here, which is proportional to the resistivity. So that's what the data looks like. The first example I'm going to show is mapping a salt dome using the Magnetotelluric technique. And this is from my PhD thesis. And this is mapping a salt dome at Gemini Prospect, which is located in the northern Gulf of Mexico. This is a natural gas prospect that's been drilled by Chevron Texaco. It was actually a little bit of a disappointment to them because they were really excited about it at first because it was the first deep water petroleum prospect that they drilled, and they were all excited about it, and then it hasn't been producing as much gas as they thought it would. But because it isn't that exciting to them, they were able to let us go there and collect data and give us their data, because there's no secrets to hold here. It wasn't working that well. Okay, so Gemini is a salt structure. It's got a very complex 3D shape. I'll talk a little bit more about that. We've been going to Gemini since about 1995, so it's where we developed our EM receiver. It's the test location for it. It was a test to map out these salt structures, the base of them. Okay, so this is the location of Gemini Prospect in the northern Gulf of Mexico. I've exaggerated the topography on land and the seafloor here just to show you the roughness of the seafloor. This region here is the continental shelf region offshore, and all this topography here, these little bumpy, wavy features and holes, is all from the tectonics of salt. And this is, I mean, it really is salt. It's like crystalline salt that is buried in the sediments, and the salt is less dense than the surrounding sediments, and so the salt tends to rise up while the sediments sink down, and it causes this funny-looking topography on the seafloor. And so here's a map showing little black blobs wherever there's been salt imaged in the Gulf of Mexico. And these are salt features that are usually tend to be at least a kilometer or two thick. And so you can see that the salt features really match the shape of the seafloor here. Okay, so now I'm going to show just a quick cartoon of how these petroleum reservoirs are formed. So during the initial formation of the Gulf of Mexico, sea level was rising and lowering, and that left behind some evaporation deposits, which evaporated the sea, and that left the salt behind. Later on, more sediments were deposited in the Gulf of Mexico, and the Mississippi River left some very organic-rich sediments on the seafloor, and that's shown as this layer here. Those organic-rich sediments were buried deeper and deeper throughout time, so this is going through millions of years. And as the sediments were buried more and more, the salt started to rise up and deform the sediments around here. And the deformation of the sediments tends to form traps, so regions where the oil can migrate in and it might be capped by a layer that isn't porous or something like that. Okay, so I'm going to show you a quick 3D visualization here. So Gemini has been a nice place for us to work because we have lots of seismic data to compare how the electromagnetic data works. And this is a bathymetry map, so this is the shape of the seafloor around Gemini, and these red dots are where we've collected our electromagnetic data over this little bump. So you see this bump in the topography here. And now my friends at Chevron Texaco have supplied me with a map based on the seismic method of where the salt is beneath Gemini. So this gray blob here is the salt feature that was imaged using the seismic method. So you can see that there. So it's got a pretty complicated shape, but we have lots of sites of data shown as these red squares that have been collected above this feature. Okay, so let's see, we've collected a total of 42 sites of data, and I'm going to present, this is a map of the 42 sites that we collected. I'm going to present the results of modeling this line of data and this line of data here. So this is a little bit confusing at first to look at. What I've plotted here now is the two lines of data the two lines that I showed you in the previous map, and I've plotted the resistivity map as the blue and red colors here, but then I've also overlain it with the seismic data that my buddies in Chevron Texaco have given me. And so one thing you can see here is this bright black line, which is the reflection of the salt in the seismic data, and that correlates well with this highly resistive zone here. And you can see a similar feature in this line here. So we're getting a resistive structure where the salt structure is, and it seems to correlate really well with the seismic data. And I'll take a step back here and give you another one of these 3D visualizations. Let's see here. Let's see here. Okay. Okay, so here are those two models. So it's the combined seismic data and the magnetotelluric data here. So, okay. So again, you can see that the bright black reflection of the top of the salt, and then this one here is the base of the salt. And we're getting pretty good agreement with the resistivity model. So we're getting the blue resistive feature here. one of the other things we see is the resistivity increases deeper down. And this is where the so-called basement of the sedimentary section here. So you have sediments above here and then more crystalline rocks down here. Crystalline rocks tend to be a lot more resistive, or blue on this map, than the sedimentary rocks. And let's see here. One of the benefits of using this electromagnetic data on here is that the seismic method tends to be really good at picking out horizontal features. So features where the seismic rays go down and bounce back up. Features that are steeply dipping or nearly vertical don't tend to reflect a lot of seismic energy back. So this is one of the strengths of the electromagnetic technique, where we can image this little overhanging ledge here, shown as this blue feature, and then it's very steeply dipping here, and we're able to image this with the electromagnetic method, whereas you don't see a very strong reflector in the seismic data here. And so using this electromagnetic data, we're able to map out where this salt feature is and correlate that with the seismic data, and that gives us a lot stronger of an interpretation of what the geology is here. And so a petroleum geologist would look at this, and based upon the different resistivity values and the seismic data, they try to take a guess at where the most likely region for a petroleum reservoir would be. And the last thing I'll end with for this part of my talk is this little yellow layer here is something it's slightly more resistive than the rocks beneath it or above it, and it's something that the seismologists have, and the petroleum people at Chevron Texaco, it's a feature that they didn't notice until we collected our electromagnetic data. And it correlates well with these slightly rougher layers here in the seismic section. And this may indicate that there's actually another petroleum reservoir at a shallower depth than the one here. The petroleum reservoir at Gemini is located at a depth of about right around this region here. And this increase in resistivity may be because there's oil in the sediments here, but we need to do some more work here to actually to actually constrain that better. So it's one of the benefits of using this electromagnetic technique is that in the seismic method you can see the layers. Well, in the electromagnetic technique you can see what's contained within the layers. So the last thing I'm going to talk about really quickly is using this magnetotelluric method to explore the magmatic system at a mid-ocean ridge. So this is something I did for my PhD thesis also. Our study area is along the East Pacific Rise, right here at about 9 degrees north. And this is a fast spreading ridge. The Earth is, the plates are diverging here, and magma is erupting here, and it's forming new crust at a rate of about a couple inches a year. Okay, so here's a close-up of the bathymetry of this ridge here. So this is the shape of the seafloor along the ridge here. And this right here is what we call the axial summit, and this is where the lava erupts along this linear feature here. And I'll go in a little bit closer here. The white line is where high-resolution mapping has determined where the crust is actually cracking apart and the lava is coming up. These orange symbols here show where there's hot water percolating out of the crust. So you have lava erupting, lava contained within the crust somewhere beneath the ridge here, and that lava heats up the seawater, and the seawater comes rushing out of the seafloor here, and it's about 350 degrees centigrade when it comes out along the seafloor. So we've collected our electromagnetic data at a couple sites shown as these squares here, these gray and white squares here along the ridge. This was a test of using this method, so this was our pilot experiment for using this method. And the seismic data from this area of the ridge indicates a region shown, this is 0 to 10 kilometers depth here and about 20 kilometers wide. It shows a region of low seismic velocity beneath the ridge, and this is associated with the magmatic system. So this low seismic velocity here is where there's assumed to be lava or partial melt magma contained within the crust. And so this is the result of our pilot experiment using the data from these 4 sites here, and we get a resistivity versus depth section here. And we get very low resistivities in a similar region to where the seismic data does. As I showed in one of the earlier slides, molten basaltic rock has a very low resistivity compared with the solid rock that's located to the sides of it. So this is our model here shown beneath the seafloor. I've put on some of the contours of seismic velocity from the seismic experiment, and you can see how well the the region of lowest seismic velocity, shown as this dashed line here, correlates really well with the low resistivity zone. And so we can use this to infer how much melt is contained beneath the ridge axis here. And we can also infer where the seawater is percolating down into the crust and getting warmed up by the lava here, or the magma, and then rising back up to the ridge where these hydrothermal vents are. And so these low light blue colors here, which are sort of medium resistivity values, are regions where seawater is probably percolating down into the crust, being warmed by the magmatic system here, and then it travels back up to the seafloor to erupt, or to be spit out at the hydrothermal vents. Let's see here. Okay, so I'm gonna show one more thing here. This is the last slide. Oops. So that was the pilot experiment that I did as a graduate student. And last year, my advisor and I were funded by NSF to do this experiment, which we're going to do in 3 weeks. We're heading back to the East Pacific Rise, and instead of collecting 5 sites of data, we're going to collect 60 sites of data, shown as these squares here. So we're going to have a really, really large profile along this portion of the ridge, and then also a smaller profile along the region where we had gone before. And so we're going to be out on the RV Ravel, one of Scripps' ships. We'll be out on that ship for about 35 days collecting this data. And that's it. I'm gonna end there. Any questions?
Can I just make a comment? I think it's pretty obvious why Kerry won the visualization contest at IGPP's Visualization Center from his talk. So.
It's a lot of late nights on the computer. Okay, why don't I start here and work my way back.
I understand you to say that the water coming out of the ridge is at 350 degrees centigrade?
Yes.
Does it come out then as a fluid or as a vapor?
It comes out as a fluid because the pressure is so great at those depths that it doesn't.
It usually explode out.
It comes out really fast. There's, people have, other scientists have, gone down in manned submersibles and put sensors and such around these vents to measure the temperature and the rates that they come out, and they come out really fast. And one of the things that happens with this hot water, when it circulates throughout the crust, it picks up a lot of minerals and such from the crust. And so when it comes out, you have this 350 degrees centigrade water coming out into the ambient ocean temperature, which is about 1 degree centigrade. And these minerals that are in the water precipitate out. They solidify right away. And so the water comes out as, it looks like black smoke. So they call these vents black smokers. It's a pretty dramatic looking thing. Next question.
What's the size of these instruments you're going to deploy? 60 of them, you say, in one line?
Yeah, correct. Okay, the question was, what's the size of these instruments? And the instruments, as I showed before, the whole frame setup is about, maybe 2.5, 3 feet tall or so, and then the arms that stick out on either side, or on all sides of the instruments, are about 5 meters long, or total about 30 feet.
And you said 200 kilograms of concrete?
Yeah, the anchors are 200 kilograms each. So,
What's the dimensions of that?
the anchors are about 4 foot square. So they have a stainless steel frame in them that we attach the instrument to. Okay, next question.
Going back to her question about the water coming out of the fissures, the work on Loihi, which is the volcano that will break surface in 10,000 years off the coast of Big Island of Hawaii, they were really noticing fresh water coming forth rather than seawater. Have you noticed that as well?
Okay, the question was that on Loihi, which is a seamount that's forming offshore Hawaii. It'll be the next Hawaiian island in several tens of thousands of years. The question was that they observe fresh water coming out there along the seafloor, and do I observe that at this region? Well, that's actually not a field that I study. I mean, I don't study the hydrothermal venting that closely, but I don't think that they notice it being freshwater here, and I suspect that the reason why they would in Hawaii is because you have land close by, and maybe there's some deep pathways for the surface waters on the land to percolate down into the seafloor. I mean, that may be the answer. I don't really know. Okay, next question.
It appeared superficially that the resolution and sensitivity of your electromagnetic method was inferior to the seismic in some sense. Of course, you had the vertical sensitivity, the seismic didn't. But what about the comparative costs and time required in the two? Can you put that in?
Okay, yeah, the question was that between the two methods, the seismic method and the magnetotelluric method, the seismic method appears to have a higher resolution than the electromagnetic method, but what are the comparative costs? Well, you're right about the resolution. Just a quick comment on that is that the seismic method is governed by the wave equation, and the electromagnetic method, the governing differential equations or diffusion equations, and those have a lower inherent resolution, but we are mapping different physical properties. So in some sense, the resolution is comparable because we're mapping a different property of the Earth. In terms of cost, it is cheaper to do the electromagnetic experiment in the way that we've done it. If a petroleum company was going to go out, they would collect 200 to 300 sites instead of 42. And deploying that many sites, at several $1,000s per site, you're talking of getting into the millions of dollars, which is about what it costs to do a high-resolution 3D seismic survey. So it's about a comparable cost if you were to do a very large-scale experiment. Yeah, next question.
I'm interested in the mechanics of that anchor. You showed it's flat. Does it have to be flat, or can it be at an angle, because the seafloor can't be all that level?
Yeah, correct. The question was why is the anchor flat as opposed to having like a tripod or other type of shape? And yeah, you're correct. We chose the flat anchor because we initially developed this instrument for petroleum exploration on the continental shelves, and that's typically in very heavily sedimented areas where the seafloor is very muddy and such. And so having a flat concrete anchor, when the instrument hits the seafloor, it just sinks down and settles into the sediments. So since the sediments are so soft, it can sink right in. On a place like these Pacific Rise here, you can see how rough the seafloor is. And it may be better for us to use something like a tripod type system here to better situate ourselves. But based on the results of our pilot experiment, we saw that these flat concrete anchors worked just fine. Next question.
Yes, I was wondering if there's a particular reason why you chose that area to study for your next experiment, and if so, what do you expect to find?
Okay, the question is why we chose this area for our upcoming experiment. This experiment is funded through a program called Ridge 2000, which is an NSF program to study the mid-ocean ridge systems in the world. And they have selected 3 focus areas in the world, so 3 different ridges. And this segment of the East Pacific Rise is one of their focus areas. And it's a pretty interesting area. It's sort of seen as like the sort of typical fast spreading ridge. So this ridge, the plates spread apart pretty fast. And the idea is that there's been a lot of experiments here. I mean, this is probably the most well-studied section of mid-ocean ridge in the world. And the idea of doing more experiments there, to some people seems, seems like overkill. But instead of going to a new place where we know nothing and just doing one experiment, we're going back to a place where we already know a lot so we can form more conclusive answers. So instead of going to a new place and saying, well, we got this data, it might be this, we can go back here and say, well, we have all this data, we know it's not this, now we have new data, so we can better answer the questions that we're trying to solve. Next question.
Back to the very conceptual question about the flat concrete.
Great.
Is there any polarization, degradation of the data if things stand on its side?
Yeah, okay, so the question was what happens if the instrument is standing on its side? Is there a degradation of the data? And the answer to that is yes. The fields that we measure are the sort of primary magnetic field is mostly oriented in the horizontal direction. There's not a lot of vertical field. You only get a vertical magnetic field if you have a strong conductivity contrast, some 2 or 3 dimensional structure. So if the instrument is tipped on its side, it's not going to measure that strong of a field. And so yeah, you're correct. And we have noticed before that one of our instruments did land a little sideways.
How do you know? Is there a level indicator?
We have a inside our data logger. We have a mechanical or an electronic compass that measures the Earth's main magnetic field, and it's a very low resolution sensor, but it's good enough for measuring the main magnetic field, and that also has a tilt meter on it, so we can tell. Yeah, next question.
How long does these packages take to drop to the bottom?
Okay, how long does it take for the packages to drop to the bottom? They sink at about 50 meters a minute, so in 100 minutes we can go down about 5 kilometers or so. So it's pretty fast. I think they slam into the seafloor. Yeah.
Spirit.
Yeah. Next question.
Yeah, in your imaging of the spreading center, the apparently molten area was fairly shallow with no connection to deeper regions.
Okay, yeah, the question is in this experiment here, the partially molten region is fairly shallow and it doesn't seem to show any connection with deeper regions. And the answer, I mean, you're exactly right. It's very observant. That's one of the questions that we're trying to answer in our upcoming experiment. So, whoops. So, let me zoom in here. Okay, so this conductive region here is very shallow. This region here is called the crustal magma body. It's the crustal level of magma, and it's inferred that the magma is coming from deeper down in the Earth's mantle. So beneath 10 kilometers and deeper, it's inferred that the lava is coming from there. Unfortunately, with our experiment, we don't have our sites for this initial experiment. We're only spaced really closely about the ridge, so we don't have that good a depth resolution or lateral sensitivity to the larger, deeper structures. And so on our upcoming experiment, we've created this profile here that's 200 kilometers wide. So these sites here, and that's one of the targets that we're trying to see is where is the melt coming from? And we know it's coming from somewhere in the mantle, but is it a narrow column that rises up from deep in the mantle, or is it diffusing in from a very wide region into the very narrow region in the crust?
Have you assessed what happens to the microorganisms and bacteria when you use this electromagnetic?
Okay, the question is what happens to the the biological organisms and such when we use this electromagnetic technique? Well, we haven't actually studied that, and it's nothing that wouldn't happen if our instruments weren't there, because we're measuring natural source electromagnetic fields. So these are fields that are going through this room right now. So they're not fields that we create. They're passive instruments. We do have another technique where we actually tow an electromagnetic transmitter along the seafloor. It doesn't have the same depth sensitivity as this technique does. It can't sense as deep, and we're actually in the process of studying the biological effects of that transmitter. So, but the electrical current densities are so low that it's probably negligible, unless you're actually to sink your teeth into the electrodes or something. Next question. Okay. Well, thank you.
Thank you, Kerry.